I'm Jannat Bedi and I'll be presenting a short video on my final year project, Multi-Agent Deep Deterministic Policy Gradient Algorithm for Swarm Systems. Now let's begin. I will first cover a brief introduction to my project, then I will touch upon swarm systems and the Multi-Agent Deep Deterministic Policy Gradient Algorithm or MADDPG. I will then walk through the implementation and wrap up with a concise conclusion. Reinforcement learning, or RL, is currently one of the most researched topics all around the globe. However, most of its success lies in single agent domains, which is why we are still far from developing artificial agents capable of demonstrating human like adaptive behavior and open ended learning, as numerous essential applications involve multiple agents and swarm systems. This is mainly due to traditional reinforcement learning approaches such as Q learning or policy gradient being poorly suited to multi agent environments. Thus, this paper puts forward an existing general purpose multi agent learning algorithm known as the MADDPG algorithm and further extends it to swarm systems via parameter tuning. The feasibility of the said algorithm is tested throughout the implementation of the algorithm for swarm systems for various environments such as cooperative communication, cooperative navigation, keep away, physical deception, predator prey, and covert communication. Now, what are swarm systems? Swarm systems are decentralized, self organized systems that can move quickly in a coordinated manner. Swarm systems consist typically of a population of simple agents interacting locally with one another and with their environment. The inspiration often comes from nature, especially biological systems. As a group, simple creatures following simple rules can display a high degree of complexity and creativity. Examples of swarm systems in the natural environment are a swarm of honeybees, ant colonies, school of fish, and flock of birds. The MADDPG algorithm implements the deep deterministic policy gradient algorithm for multi agents with centralized training and decentralized execution. It can be considered as a simple extension of actor critic policy gradient methods where the critic is augmented with extra information about the policies of other agents. The given slide shows a snippet of the MADDPG algorithm pseudocode. The MADDPG algorithm was modified to accommodate the more complex swarm systems. For this implementation, the agents were decreased in size and range and increased in number. For certain environments in different locations, the size of landmarks were also altered. The reward and algorithm were modified in accordance with the changes made for agents and landmarks. A great variation of environments were implemented with the modified algorithm. Let's briefly go through how each of them were implemented. In the cooperative communication environment, the two speakers observed the goal of other agents. Each listener communicated with the speaker and then navigated towards the correct landmark accordingly. In cooperative navigation, a landmark was considered occupied only if there were at least two agents within the minimum distance threshold. In our case of two landmarks and four agents, two agents occupied each landmark while trying to avoid collisions. For keep away, the adversary learned to push both the agents away from the landmark. In the case of physical deception, all agents observed position of landmarks and other agents. The agents learned to deceive the adversary by trying to cover all landmarks, making it difficult for the adversary to figure out the target landmark. For predator-prey environment, the faster adversaries tried to tag the good agents while the slower good agents or the prey tried to escape from being hit by the adversaries, all the while avoiding obstacles. For covert communication, the private key was shared by the speaker and the two good listeners, while the two adversaries tried to decrypt the message sent by the speaker. In conclusion, it can be said that the MADDPG algorithm can be extended for swarm systems on a smaller scale with low levels of complexity, considering that the environment, algorithm, conditions, and reward functions are adjusted appropriately. This brings us to the end of the video. Thank you for your time.